All right, so how are y'all feeling about everything at this moment?
Pretty good.
I can tell you what I normally see out of my test. I see people who really get it, and they do really well on the test, and I see people that actually get it, but struggle on the test because they don't factor well. Like, you have to know, if you're checking and correcting your work, and you're missing stuff because of factoring, just listen. Tell your parents if you don't drive, I need to be there early one day, I need to come after school. The factoring's not that bad anymore. It's not going to be brutal. You're not going to see stuff where you get like, where there's no GCF and you have these brutal big composite numbers on the end. You don't see that anymore. I mean, normally if there's even a number on the front, it's like a 2x squared. Or most of the time it's just an x squared something. And maybe it's a difference of 2 squares or a perfect square trinomial or something like that. But the factoring's never going to be real brutal for what we're doing. But ultimately you still have to know how to factor. And I think you guys, if you're struggling with the factoring, when you accidentally do stuff, like let's just say I had, I don't know, like this is one that gets people a lot. They look at this and they go, oh yeah, x minus 6, x plus 1. That's the right answer. But I have people all the time that go x minus 2, x minus 3. And they go, why? Because negative 3x and negative 2x is negative 5. But then it would be positive 6. And the reason why they're missing that is they're just not checking the FOIL. If you think that's a good guess and you feel about it, check the FOIL, right? X squared. Negative 3x, negative 2x is your outside, inside, negative 5x. Positive 6, that didn't work. Try something else. But a lot of times the mistakes, and if that mistake happens, then nothing cancels probably, and it's just this snowball of errors that continues. Or you can't solve it, which is what we're going to be doing today, a little bit of, and some fun work problems.
I did have a question on one. I forgot my book, but it was number 28 on page 239.
Yeah. So 28. Oh, yeah. Good question. The question is,
whoa, wait.
is it this thing?
Yes.
Where they gave that, it said express that as a single simplified fraction, and number 28 was if f of x is 1 over x. Now, let me ask you a question. What would you have done if I said express this as a single simplified fraction? What would you have done? I said, if this is your function, right, and I want you to do that, what would you have done?
4f minus 2, so 2f over h or something.
Oh, how do you find f of 4? If this is your f of x, you plug a 4 in? So you would have done that maybe? And then how do you find f of 2? You'd have plugged the 2 in, and then you would have said, okay, 1/4 minus 1/2 over h. That's what you're doing, except it's just not pretty. You're not finding f of 4, you're finding what? F of x plus h? I don't know what the heck I do know what it means. This is the building block of calculus. And they're trying to sneak it in here to kind of imprint your brain with information. So when you get to calculus, you go, oh, that's the definition of the slope of a secant between 2 points.
It had like a notation like this. It said like calculus.
Oh yeah, these exercises might be in calculus, yeah. It's been so long I didn't notice that. But right here, I need to find this, and then I need to find that, and then I need to subtract them and put them over h. So let's do it. What is f of x plus h? Well, according to this, whatever you have here, you put it there. So whatever I have here, I put it there. Well, I don't know what to do with that, but I have it. And then, how do I find f of x?
It's just the same thing.
Well, it's just the same thing, right? 1 over x. So I am to do this then, I'm going to take what I found for the f of the x plus h, and then I'm going to take what I found for the f of x, and I'm going to divide it by h. And that's why this is in this section. Because I gave y'all a hint in the video about what to do if you have a fraction inside of another fraction. You could and we did this at the end of the period in the video, you could find common denominators and add this or subtract this stuff together. And then to have a number divided by another number, to divide, you multiply by reciprocal. I could totally do that. But what was the hint I gave you? Really helps. Find the LCM of these three numbers. So what would the LCM be of that, and that?
X plus h times x times 1.
X plus h times x times 1. And the 1 is irrelevant, right?
Yeah.
So multiply the top and the bottom by x plus h, and 1. And why can I do that? Because multiplying the top and the bottom is the same thing as doing what?
Divide 1.
Multiplying by 1. Like if I multiply the top and the bottom by 3, I'm multiplying by 3 over 3.
Yeah.
So when I multiply the top and the bottom by that, I'm multiplying by that fraction, which is 1. So it's going to change the look, but not the value. And that's the key, right? Now, here I'm multiplying this times all of this. So you're going to have to distribute it in. So a lot of times I like to distribute it in so I see it right there. Now, what cancels in this expression? And I'm left with 1 times x. Let me bring that down. And then I'm going to bring down the negative. And what cancels in this expression? That, and I'm going to bring down the x plus h, except I'm going to remember to put it in parentheses because I have to distribute that negative in there. That's probably the biggest mistake. People forget the parentheses. And then I'm going to divide it all by what?
H. Or x plus
H.
X squared plus hx.
Don't even multiply it out. Just leave it like that.
Okay.
Now, does anything clean up here?
X minus x.
So when I distribute that negative, I get x minus h
Yeah.
over h, x, and x plus h. Right? And what cancels?
The x cancels and it's just a negative h.
And then you're left with that. And then what else cancels? Yeah, now that the x's are gone, the h's cancel. And leaves you with what though?
Negative 1 over x times x plus h.
So negative 1 over x times x plus h.
Okay.
Now, if this were calculus, this is what you'd be doing. Find the limit as h approaches 0 of this. And that is the definition of a derivative. And a derivative is the slope or the rate at which things change, which is one of the more used topics in math, science, financial analysis. Finding maximums and mins. If slopes are changing on curves, what happens at the top? What's the slope?
Max.
Looks very zero-ish, doesn't it? Slope of 0. And then it changes to the bottom of the curve and it's 0. What if that's a profit curve? I want to know how I maximize profit. So I'll take a derivative and I'll find what the slope is 0. And some of those zeros give me max, some of them give me mins. And I have to do a little bit more analysis to make sure my company isn't designed to lose, right? I want to win. But I might find that, hey, some part of the function I maximize here, but if I really grow the company more, it might maximize here, and I can do analysis and figure out what do I need to do to change these things to maximize my profit or minimize my costs. The derivative is used in so many applications. In physics, I can take a position function, take a derivative, and now it's a velocity function, or like a speed function. I can take a derivative again, and now it's an acceleration function. And it's all based on that, except we learn tricks so we don't have to do this terrible math all the time. But if this was a function, 1 over x, when you take the derivative, when this is what you would do manually, you would simplify it to here, and then you would say, oh, the limit as h goes to 0 of this. And that basically means now, plug a 0 in, and you get negative 1 over x squared. And that's the derivative of this function. Now you're going to learn to take the derivative of this function. You're going to go straight to that and go, oh, negative 1 over x squared. You're going to have a little rule memorized that helps you get there to avoid all this. But you just did a little calculus today, didn't you? Except that I want to train you so you don't have to do this. So my guys, we mentioned this for a couple days and they're like, ugh. And if you take Cal 1 at Auburn or Alabama, a lot of times the teacher goes, no, we're doing this all year, dude, or all semester. Which is why you want to do well on your AP test so you don't have to go through that minutia. It's so annoying in Cal 1. And jump straight to your rules and your applications. But anyway, that was just a taste of that. That was 28 on your homework for those of you at home. Good question. All right, but you're going to see that over and over again. I'm going to be talking about that function. You're going to come back to it. So 2 years from now, actually not even 2 years from now, end of the year next year, if you're in this class, or even in regular pre-cal, I think they talk about it as well. If you decide this is your last swan song in math team, which is fine. Anyway, if you go to where we are today, actually, you're going to be in the book on page 111, but before we get there, I want to talk about this. So, what if, I'm jumping back to yesterday, I gave you this. This is not in the book. And I said, add these. Now, this is not an equation, is it?
No.
If it's not an equation, you can't solve it. There's no x that makes this true because it's not a statement about truth. It's just an expression. Okay? So, in order to add these, I would be forced to do what? Find a common denominator. And finding common denominators, as you know, is all about just tweaking these numbers so that they match. But whatever I do on the bottom, I'd also have to do on the top. Now, if you don't need to do a prime factorization, like I think everybody in here just looks at that and knows that the least common multiple is 30. But a lot of people make the mistake of going, oh, why isn't it 150? Well, 150 is a fine common denominator, but it's not the least common denominator. And you will find that if you pick the least, it's going to make your life much easier in the end. So I'm always going to kind of, if I can eyeball it, great. If I can't, do a prime factorization. But here, to make these common, what do I got to do?
Find prime factorizations.
Well, if you know it's 30, what do you need to do to make it 30?
2 and 2, and then
2 and 2 and
3 and 3.
3 and 3. So if you can eyeball it and know that it's 30, make it 30. All right? Now that gives me 4x plus 3, right? 1 times 3 over a common denominator of 30. And you would be finished at that point. All right? Now, what if instead of giving you this, I gave you this? Now it is a what? An equation. And now I probably would be telling you to solve. And because it is an equation, guys, this is such a big deal what I'm saying. I don't know how else to emphasize to you that if it's an equation, your ability to manipulate stuff changes because of algebra. Algebra is all about what? Maybe you don't know this. Algebra is all about keeping equations in balance. And you have all kinds of rules, right? Like I can add 4 to both sides. I can divide both sides by 7. I can square both sides. Because if they're equal, then doing one thing and doing the same thing to the other side still makes them equal, right? I can't do that when it's not an equation. I'm forced to just change their look but not their value. So if I start you with this problem and it's not an equation, the only way I can simplify that is to find a common denominator. But what if I start this problem and it is an equation? Then I don't have to do this, because now I'm allowed to do one thing to one side and one thing to the other side. And because I have that gift with equations, what could I multiply through that would get rid of these denominators? What one number? And you know what? That number is the least common multiple of all 3. And what is the least common multiple of all 3? Still 30? And again, if you didn't see it, then break it up. 5 and 3, 2 and 5 and 2. Highest power of 2, 2. Highest power of 3, 3. Highest power of 5. So 30 would be my LCM. Well, instead of finding that common denominator and adjusting the fractions, I'm just going to multiply. What's algebra? Does algebra say multiply each term or multiply both sides?
Both sides.
Okay, so I'm going to multiply that side and that side by 30. But what does the distributive property say? To multiply it in. So because I can multiply it, I'm going to do that. Now, did I do anything wrong algebraically? No, but look what happens now. Now I can cancel the 15 with the 30, leaves me an extra 2. I can cancel the 10 with the 30, leaves me an extra 3. I can cancel the 2 with the 30 and leave me an extra 15. And I'm left with 2 times 2x. I'm just going to write this out. Plus 3 times the 1 equals 15 times the x squared, which can clean up really nicely, right? And at this point, we're back in our last chapter. Now, right here, yes, you've got to be able to factor. Subtract that 4x. I tend to like to keep the highest power positive. I think better with factoring that way. Minus the 3x. And you're going to have to play around with this or use your magic number. I had somebody in my 5th grade class go, dude, I use magic number on anything. I don't care how long it takes me. I'm never wrong. I feel comfortable with that. Great. Do what you got to do. But if you want to guess, check, and revise on these, you can say, all right, maybe it's a 5x and maybe it's a 3x. Maybe it's a 15x, maybe it's a 1x. I don't know yet. And then you keep playing with it. You go, oh, maybe it's a 3 there and a 1 there. And you're still guessing, right? Because 15 could be that. 3 could be that. But let's check the FOIL. Is there any way I get a negative 4 out of this? 5x and 9x? No?
Wait, yeah.
I would get a negative 4 if it was a negative 9 and a positive 5, wouldn't I? Right? Positive 5x, negative 9x. But let's check the whole thing. Negative 3. Feel good about that. So x equals 3/5. X equals negative 1/3. Go with me? Do I have the freedom to do this if it's not an equation? I do not. Every day, not every day, every year I give this test. And I have a problem. It's not an equation. It's a bunch of fractions that are ugly and people multiply through. Literally, what happens if you have an expression and you just multiply it by something? It's now a different value, isn't it? Not only does it look different, but it has a different value. If I could go around multiplying stuff all the time, where would I go? Where would you go if somebody said, hey, you can multiply anything you want by a number? I'm going to the bank, right? I'm not sitting in algebra class. Bam! I'm good. I can do whatever I want from now on. All right, so on these, remember, you can multiply through by a number when it's an equation because that's algebra. But when it's not an equation, you are stuck using the PEMDAS and simplifying it and finding common denominators and all that stuff. Are y'all with me? Okay, let me give you a couple other ones just to make sure you're with me. Maybe I'll make them look a little uglier. And then we'll get into some word problems. So everybody's fun thing. All right, what about x minus 4 over 4? Heck, we'll put an inequality in there, mess with you a little bit. What about 5x over 12 on this side and a minus 3? Now, it is an equation because of the equal, but it's also an inequality. So if I ever multiply by a negative, what would you have to do?
Multiply the other side by a negative.
Well, that might be true, but I would have to switch the direction of the inequality.
Yeah.
Right? But I don't need to do that. Now, I look at this and I go, man, it's fractions. I don't really like it. But it is an equation. So I have the freedom not to make a common denominator of 12 and rewrite all the numerators. I am allowed to do what?
Least common multiple.
I'm still going to find the least common multiple. And it's 12. But instead of rewriting this with the 3 on the bottom, 3 on the top, 12 on the bottom, 12 on the top, instead of doing that, I can now multiply both sides by 12. And in doing that, applying that algebra rule, and then over here I go, oh, I can distribute that in, so I'll get another 12 over here. Then I can go through and just cancel it all out. Oh, by the way, don't multiply it in. Every year I have somebody do this. 12x minus 48, and that cancels and leaves me a 3, and then they get all lost in it. Why did you multiply by this? So you didn't have to divide, right? To get rid of that. Nothing cancels over there. And then bring down what you have. I did not multiply by a negative, so I do not have to change the direction of that inequality. Distribute it out. And at that point, add like terms. And I made a mistake. 5x, 36, 3x, 12. Did I?
Yeah, well, you put 3.
Oh no, that's right. I copied the problem down wrong. Based on this, that's right.
Wait.
Because if I subtract 3x, it's a 2x. If I add a
Yeah,
36.
yeah.
Yeah, in my problem, in my book, it's a 14. That's why. Are you with me? So according to this, everything smaller than or equal to 12 would work. And if you're writing that in interval notation, I would say from negative infinity all the way up to the 12. Sorry, you don't put brackets on it. From negative infinity all the way up to the 12. You okay?
Mm-hmm.
Now, they're going to get uglier tomorrow. Tomorrow I'm going to start putting x's in the denominators and things like that. But the same thing's true. If it's an equation, you have the freedom to not find the common denominator and rewrite them with common denominators, but you have the freedom to find that common denominator and multiply it through and immediately get rid of fractions. But when can you not do that? When it's not an equation. And I'm telling you, that is one of the biggest mistakes. And people do it all the way through the test. They're like, why can't I multiply that? It's not an equation. You can't just multiply randomly by stuff. If we could, we wouldn't be in here, right? Right. All right, so let's see why they're putting these word problems in this section. You might recognize some of these, you might not. We'll see. Go to your book, the book, page 111. And this will make it, we don't have to copy stuff down. So this is page 111. Do you remember these pump problems? My experience with students and pump problems is, man, I memorized that stuff, but I don't know what's going on. So let me talk about this. Do you remember the distance, rate, and time problem? Okay, and you remember, and you probably didn't love it, but you remember this part, right? Now, distance was an amount of miles, right? And when you multiply a rate like miles per hour by a time like hours, you get that amount. That's what distance is, an amount. Well, it works with any rate and time. It just depends on what my rate is. I'm not always going miles per hour. Sometimes I'm drinking gallons per hour. Sometimes I'm eating hot dogs per hour. Sometimes I am pumping out a boat in hours, but I'm actually pumping boats per hour. Are you with me? But when that rate times time is always going to give me some amount. So think about this problem, not as distance equals rate times time, but some amount equals rate times time. Now I have a question for you. You read this problem, pump A can unload the boat in 30 hours. Seems like they're giving you a time, doesn't it? And they kind of are, but it's the time it took to unload the boat. So if it takes me 30 hours to unload one boat, then that's kind of a rate, isn't it? How much of the boat am I doing per hour with pump A?
130.
Does that make sense? He said 130.
Oh.
So if I'm pumping out a boat, if it takes me 30 hours, I'm doing 1/30th per hour. You seeing that? So really, what I'm doing here is my rate is 1/30th of the boat per hour. Now, pump B, it says, can unload the boat in 24 hours. So if it takes him 24 hours alone, that's if these things are working alone, right? So if you just had plenty of time, you're like, yeah, hook up the pump B to the boat and pump out all the oil or whatever it had in it, right? It would do it in 24 hours. Man, 24 hours is a lot of downtime, right? There's guys waiting to ship that boat somewhere else. You're losing money in revenue. So you want to get that thing pumped out as much as possible. But it says it can do it in 24 hours. Well, what is its rate then? What part of the boat is it doing each hour? 1/24th an hour? So pump B is doing 1/24th per hour. And that's its rate. Now, it says working together. How long did it take? Now, if they work together, one of it is obviously going a little bit faster than the other one, isn't it? Because it takes this one longer. But if they work together, aren't they going to start and finish at the same time? Now, I don't know what that time is. You got to figure, oh, if they're working together, they're doing about half the work. Now, this guy's going to end up doing a little bit more because he's faster, right? But if they're doing half the work, I would think that my final result would be somewhere in between 15 and 24 hours. Probably 12 something, maybe 13, I don't know. We'll see. If they're working together, does that make sense? To do the whole shit? But I'm not going to worry about that because I don't know the time, but it's the same time for each. So I'm just going to put a T in there. And what do rates and times get me when I multiply them together? Amounts. And what is this amount plus this amount? This is isn't this the part of the boat that this guy pumped out? This pumped out?
Mm-hmm.
And this is the part or the amount of the stuff that got pumped out? And if you add the two amounts together, what did they pump out? One boat.
Well, because the time will always be reciprocal, right? Like the time will always be reciprocal, right?
This, yes, will end up looking like a reciprocal here. Is that what you're saying?
Yeah.
But my point is, rate times time equals amount, and the total amount, it said they were doing one ship. So In this case, if it said 4 ships, put a 4. Now, in your book, they show this, t over 30 plus t over 24, and that's what I do too. And that's what they teach you in Algebra 1 to memorize. But it always seems, why are they doing it? It doesn't seem like it makes as much sense to me. But, and it kind of does in the terms of time divided by time, cancels out. But to me, when you think about it as rate times time, it makes more sense. And this is why they put it in this section, because what do you do to solve that equation? You got to find a common denominator. But you now, because it's an equation, instead of finding the common denominator and rewriting every number with a common denominator, I have the freedom, because it's an equation, to multiply those sides by that LCM. Now this LCM is not as easy to see. Y'all see it?
120.
Maybe it is. Okay, so it is ended up being 120. If you're not able to see that, you can always do is it 30? Take the biggest number. No. Is it 60? No. Is it 90? No. Is it 120? Yeah, I can multiply that by a 5 and that by a 4, and it would be a 120, right? But if you don't know how to do that, it's 30. 2 times 3 times 5. 24. 2 cubed times 3. Highest power of each. And 8 times 5 is 40, times 3 is 120. So you can find the LCM that way, and then just take advantage of the algebra. Don't redo these fractions. Multiply the left and multiply the right by the 120. Distribute it in, which puts the 120 on both of these. Show that math, guys. If you make 94s and 98s on your tests, a lot of you figure out shortcuts. You're doing that naturally, like, why don't I just multiply that by 120 and that by a 4 and that by a 5? But if you don't, I see teachers teach that and people get all wigged out and they get hammered on their test. Don't do that. Show the math until you figure out your own thing. So this leaves me 120 times 1. The 30 and the 120 cancel, leaving me a 4. So 4t. The 24 and the 120 cancel, leaving me a 5 plus 5t. So I get 9t equals 120. And when I divide by 9, I know a 3 goes out of that. I get 40/3. Now, if it was a math tournament, 40/3 works. But this question said, how long did it take? And we tend to deal in hours. People don't go, man, it took me 40/3 hours to do my homework last night. Makes no sense to anybody. So what is that, really?
I think, is it 13?
13 and 1/3? And what's a third of an hour?
20 minutes.
And how did you find that other than just being intelligent?
The
If it wasn't easy to do, what would you do?
what's it called?
You would say one third of a 60 minutes,
Yeah.
right? And that would cancel and leave you a 20. So if it's not something, if it's like 1/8 of an hour and you don't know that, 1/8 times 60. And that will give you the minutes. So it takes me 13 hours, 20 minutes. Now here's what might get trickier for you. What if I said, and I didn't hear, but if I did, what if I said, if you begin at 2:30 a.m., then when do you finish? And don't say 13 hours and 20 minutes later. Like, when are you finished? At what time?
3:50.
So how do you do 2:30 plus 13? I tell you what, make it 2:50 to make it even uglier.
So,
How do you add 13:20 to that?
add them up, subtract
So,
12.
add the 0, but what happens when you add that? You get 70 minutes. What is that?
An hour and 10 minutes.
So since 70 minutes is an hour and 10, I'm going to put a 10 there, carry an hour. Does that make sense? And then you get what?
6.
6, so I get 16:10. Now, if you're in the military, that's great. My dad's a military guy. I'll meet you at 1600. Like, Dad, you're not at work. What does 1600 mean? What do you do to get the time?
Minus 12.
So you minus that 12, and when you do that, so this would be military time, but if you subtract a 12 from that, that gives you 4:10, and if this was AM, you've now jumped to PM. Be able to do that as well, although that's not gonna be a massive part of your question, but it might be a point or something like that. All right, what about this? Remember these mixture problems?
I remember she made us do like a box or something. But,
Yeah, you gotta remember, guys.
Gotta do these little-
She only, I know Susanna does the box.
All right, let me ask you a question. Well, not everybody plays baseball. I was gonna say hitting a curveball. The first time somebody, I remember it was like 4th or 5th grade, somebody threw a curveball and you were like, what the heck?
Yep.
And then after a while, you figured out the curveball and you learned to sit on it. You learned to get beamed by it and it didn't hurt that bad because it was coming in slower. And you started getting adjusted, and then pretty soon you learned to hit it. Or you phased out of baseball. Because if you can't hit a curveball, your career is kind of ending at some point because they're just going to throw you nothing but curveballs. But it's probably true like that with anything. There's some learning curve on stuff. 2 years ago in Miss Tyree's class, you guys were not the mental giants you are today. You're not. You may go, I don't feel like a mental giant. That may be true in here, but 2 years is massive in the life of an algebra person. A year, you're gonna, like, you guys come into this class as mere plebeians. By the end of the year, it is shocking what you know in comparison to the beginning. I mean, it is truly amazing. It's like, it's always been funny to me. It's like girls from 9th grade to 10th grade. Like, I see you guys, it's so funny to me. I watch you walk into Mr. Homer's class. So I used to, because we were right next door. First day of class. And you got, like, it's like you're little bitty kids. Dudes grow up a lot too. Sometimes it's from 10th to 11th. They kind of finish up or whatever. But it's amazing how you guys go from little bitty kids to like young women, like in a year. It's like I don't even recognize most of you guys. I don't even know your faces. And I've been watching you. Maybe if I know your parents or something like that, or siblings. But most of the time, it's amazing that transition just in a year where your brain's the same way. It's amazing how much. So when you see mixture problems, you're like, oh Lord, that was 8th and 7th grade math. It's going to be better. Okay, so just trust that. Now, mixture problems are kind of like rate and time problems, except it's not rate and time. It's like amount and a percent. But a percent is kind of a rate. Like if you buy gas, I don't know if you know this, when you pump your gas and you go, what do I want? Do I want the 88 octane or the 91 or the 93? Well, I don't know many people who go 93 because it costs so much more. It's like, man, give me the 88. You got West, it's 85. Well, that's a percent. 88 octane or 87 octane is a percent of purity in the gas. So 87 means 80% of that gas is good gas and the rest of it's like corn meal or something turned into some sugary solution. It still burns, probably messes up your fuel injectors, whatever, but it's a rate of purity. So again, it's kind of like a rate and time problem. Distance, rate, and time. But I think about it as amount and percent. Amount times the percent. Okay? Are you with me? So I know before we said amount equals rate times time, but it's kind of like rate and time. The amount is kind of like the time in these problems. And if I have a bunch of amounts that are being added and a bunch of different percents or subtracted, I can think about these as adding a rate, amounts, and when I get to the end, it's equal to a total amount and some weighted percent. Now, don't make the mistake of adding percents. That's like adding rates. If I drove to your house at 10 miles an hour and drove back at 12 miles an hour, was my average rate the sum of those? 22 miles an hour? No. Right? That would break physics. Same thing on percentages. If I mix an 8% sugar solution of Milo's tea with a 12% solution of Milo's tea, do I get a 20% solution? No, I get somewhere in the middle. But it's not necessarily in the middle because I might have different amounts, right? Obviously, if I take Milo's, a gallon of Milo's, and a teaspoon of unsweet tea and mix them, you're not going to notice a change, right? But it is somewhere in the middle. It's just really heavy towards the Milo's tea side, right? Well, right here, it looks like I'm adding pure antifreeze. Now, John, antifreeze in a car is something that you usually mix with water. And if you've taken chemistry at all and done solutions, when somebody says they have a 30% solution of something, like if I have a 30% hydrochloric acid solution, what does that mean?
30% of it is hydrochloric acid.
So 30% of it is pure hydrochloric acid, and the rest is like the mixture. It's like the solution, the base, which is normally water, right? Now, not with gasoline, but if I have so when I have an 87% octane gas, 87% of that is pure. Are you with me? So if I tell you that I have 100% antifreeze, right? How much 100% antifreeze? That is a 100%. That is a pure solution of antifreeze. It was not mixed with any water. And since I don't know how much, X. Now, how much of that should be added to 12 liters? Oh, they gave me another amount and told me to add of a 40% solution. So that's 40% antifreeze. And the rest must be water. And by the way, if it's 100%, sorry, don't write 100, write point. Why is that? Because 100%, what does percent mean?
Wait, what would be 1?
Oh, sorry, no, you're right. Yeah, sorry, 1. 100% means what? 100 divided by 100. 40% means 40 divided by 100. So move that decimal place two spots when you put it in there. Sorry about that. Now, when I add this together, doesn't it make sense that I'll have some final or total amount
Yes.
and some average? Now, it's not a perfect average. You could call it a weighted average, but something in the middle, percentage-wise. So what am I going to end up with? It says I want to end up with a 60% solution, so they gave me the percentage, 0.60, but what's the amount?
12 plus X.
X. This amount plus this amount is that amount. Now, if you're looking at this and going, okay, great, it's a mixture problem, but why would that be in this section? Why would it be in this section? Yeah, they're wanting you to think about this as a fraction. They're wanting you to think, oh, well, 100% really means 100 over 100. 40% really means 40 over 100. 60% really means 60 over 100. Now, do I need you to do that? No. But I still need you to think, what am I allowed to do with an equation now? Multiply it through, and this is like it's a it's like it's a fraction, right? So how would I move the decimal twice? Actually, do you need to move it twice? On this one? 60, 40?
One time.
I really need to move it 1 to get rid of decimals, don't I? So what could you multiply by?
10.
10. But if that had been like 42% or 65%, to move it twice, you'd have to multiply by 100. But in this one, I can get away with 10, so let's do it. Left side by a 10, right side by a 10. Now, because there's a big plus right here, I have to multiply 10 by this whole term and 10 by that whole term, because that's a whole term, something plus something. All right? But look, this is multiplied together. So I can just multiply 10 by just the 0.6. And that's usually what I do anyway. 10 times that moves the decimal once, 10x. 10 times that moves the decimal once, 12 times 4. 10 times that moves the decimal once, x plus 12 times 6. And then once I move the decimal, I'm back to last chapter. Right? So 10x plus 48 plus 6x plus 72, 4x plus 24, x is 6. So I need 6 liters of that to add to 12 liters of that to create 18 liters of that. Not too bad. Now I can get uglier. But I'm going to pick my... How about this real quickly, just to set it up? How much water must be evaporated from a 200-liter container of a 7% solution to obtain a 12% solution? All right, let's check it out. I got an amount and a percent. I'm going to evaporate. What does that sound like? Subtract another amount, percent, and end up with a final amount in percent. So that's the final, second, first. Let's see if we can figure it out. How much water? I don't know, X. Now water, what percent solution is water if I'm talking about other solutions? Water would be what?
100%.
It's actually a 0, isn't it? Like if I'm dealing with 7% hydrochloric acid, that means 7% is hydrochloric acid, all the rest is water. So pure water is what percent hydrochloric acid? Does that make sense? It'd be nothing. So if I have a solution, and I'd probably be a little bit more clear here, I probably should use something like hydrochloric acid in there, a 7% solution of hydrochloric, what's that, HCl? Hydrochloric acid to obtain a 12% solution. So if I had done that, water is actually a 0% hydrochloric acid solution. Does that make sense? So I'll be more clear on that. How about that? Now, I'm gonna say how much water, oh, sorry. That is not right, right here, hold on. It says how much water must be evaporated. Sorry about that. So I am subtracting the water, right? So how much water must be evaporated from what? From a
The original solution.
200 liter container of 7% to obtain what? A 7%, no, a 12% solution of what? What's my final amount?
200 minutes.
Y'all see that? 200 minus X? Check it out again. How much must be evaporated? I don't know, but it is a 0% HCl solution. That's going to be evaporated from a 200 liters of a 7%, and once I evaporate a bunch of water off, there's more hydrochloric acid left, right? So there ends up being less, but the hydrochloric acid is a higher percentage. Be like me taking Milo's tea and evaporating a bunch of water. The sugar's staying in there, right? Only the water's leaving, and if you knew how that, the water's leaving, so it ends up being a lot more concentrated with sugar and tea. Now, this ends up going away, but if I don't like those decimals, what can I do? So everything on the left by 100, which distributes into each part, and everything on the right by 100, which is going to multiply in right there, and I don't even need to distribute it after that. So this times this, 7 times the 200, all of that goes away, and then that gives me 200 minus X times 12. And at that point, you can do the math.
So that just ends up, so that one just ends up being 0.
Yeah, ends up being 0. But for people who go, well, why are you bothering? Well, writing it out, look, that 200 and that minus X helped me to find this part. So that's where it comes into play. So you can't just like ignore it, or you think 200, 200. But I did get rid of something. Let me give you a little formula on this last one because I'm kind of running out of time and I don't want to talk a little bit about this very last one. I ran up a hill and down the hill at the same rate. It's really easy to think, oh, if I go up a hill at 12 and down a hill at 16, I must have averaged 14. Now that'd be true if I did this. I ran for an hour at 12 miles per hour, and then I ran for an hour at 16 miles per hour. What was my average rate? But because my times were the same, right, then that would be 14 miles an hour. That would be true. But here I'm not saying that I did it for the same amount of time, right? If you're running up a hill at 12 and down a hill at 16, didn't you get the second distance done a lot faster?
Mm-hmm.
So you spent less time there at that rate. Are you with me? So that's going to affect it, and it's not going to end up in the middle. Now I could show you a big distance, rate, and time problem for this, but I have simplified it into a nice little rule. Okay? So if D1 equals D2 on these distance, rate, time problems, and I need to know average rate, my average rate is always going to be 2 times the product over the sum. 2 times the product of the rates over the sum of the rates. If I have time, I would show you, but I don't have time right this second. So right here, to find the average rate, 2 times product of 12 and 16 over the sum of 12 and 16. And I need to clean it up, so I'm not going to multiply that out yet. 12 and 16 is 28, and I can cancel a 4 out of that and a 4 out of that, and I get 6 times 16, which is 96 sevenths. And if you did the math on that, which I don't need you to, you get 13 and what? And 5 sevenths, which is not quite 14, is it? It's a little bit, what? Closer to that because I did that so much longer, it slowed me down. It's not dead in the middle, a little bit smaller than that. But you're fine to leave it like this, honestly. And you ought to put miles per hour in there as well. Little formula. If the distances are the same. If they're not, you got a distance, rate, and time problem like we did earlier in the year. So you'd have to do like, R1 over, R times T plus R times T. It'd be really long and involved. But if the distances are the same, going there and coming back, and it doesn't even have to be coming back. It could be, I ran the first half of my trip distance-wise, and then the second half of my trip distance-wise. Even if going from A to B and then beyond to C, if the distances match, average rate is always that. All right, last thing, real quickly. Probably won't have time to do all of this, but just real quickly. Is there any difference here? Same kind of problem. Biff can cut the yard in 4 hours, so his rate is 1/4 per hour. Buffy in 5 hours, her rate is 1/5 per hour. I'm starting this problem and I'm cutting 1 yard, right? But what's different? Biff begins at noon, Buffy starts at 12:30. So they don't share the same amount of time cutting the yard, do they? So what do you do with Buffy's time? She worked what? 30 minutes more or 30 minutes less? Less? Now can I put 30 minutes in there if these are miles per hour? But it would be a half an hour? So that's Biff's time. Buffy's time would be T minus a half. And at this point, you're back basically doing a pump problem. Does that make sense? All right. Well, good luck on these tonight. Bring your questions on, oh, well, I won't see y'all till Tuesday. Bring your questions on Tuesday or email them to me, and we'll try to get you squared.